This video describes how to use support vector machines in R. We're going to use support vector machines to make a spam email detector. And the way that we're going to do this is using the E1071 library and the support vector machines that it can make. So let's get started. First of all, we need to get our libraries loaded. So we'll get the tidyverse library and the E1071 library. Okay, now the data is from the KernLab package, and it's appropriately named. It's called spam because it's about spam. Now the structure of the data in question we'll see in a moment, but basically each row in this data frame, the spam data frame, consists of an email message, and each column is a normalized word frequency for a whole bunch of different words, with one exception. That one exception being that there is a type column that tells you whether that email message was indeed spam or not. Well, in order to run this as a systematic study, we should split this up into training, query, and test samples as per the process that we described in the previous video. So let's make a sampling frame, a raw data sampling frame. Let's take our data and we're going to split it up. The way that we're going to split it up is by way of adding a new column, which we'll temporarily use to help us identify our samples. The way that we do this is by producing a random number for each column. So reorder the columns randomly and then normalize them so that that column lies between 0 and 1, and then we can very easily select out various fractions of columns randomly. Now, as it turns out, there are two columns in this data set that turn out to be a bit, make the data a little too easy. Because this was back before the days of spear phishing, wherein a spammer or phisher would actually successfully impersonate someone inside your organization. So to make this a little easier, we're going to remove two columns. This is a little bit of a violation of data process, but the results tend to be a little harder this way. Okay, great. So we've pulled out those two columns that make it the data a little too easy. All right, there's our sampling frame loaded up. You can see that we've got same number of observations, different number of columns. Why? Because we've added one and removed two. So we've gone down net by one. Let's pull off our data. Our training data is going to be our sampling frame. And we're going to filter out the first 60% for training, and we'll get rid of the temporary snum column that I just created. So that's our training data. We'll make our query data to be everything which has got an snum between 0 and 0.6. And here's our test set. Our test set is everything. It's got an snum greater than 0.8. Okay, great. Now, at this point, you should save these guys all off as CSV files. Watch the previous video for how to do that, and make sure you submit them to Canvas because they'll be important for grading. Now, as it turns out, the support vector machines run a little bit more nicely in some cases if we can split out the truth, i.e. the response variable, is this spam or not, from the explanatory variables, i.e. all the normalized word frequencies. So to that end, let's peel off the type column, which is the column that's got the correct answer in there, into two separate sets, the input set And so the input set will have no type column. Oops. Okay, that's the input, and similarly for the others. So we'll put the query in there. And finally, the testing. Guess I called it test, not testing. Okay, and all right. So now let's go examine. Well, we've got our training data peeled off, so it's legitimate to look at our training data. You can see what our training data look like. Each row is an email message. Each column are some normalized word frequencies. You can see most of them are fairly small, but every now and then again you happen to hit one. There's one. And various other properties as well. Okay, great. So now the question is, what does this look like? Well, I think since you've got all this big table of numerical data, PCA is the way to go. This is one of those handy reasons why we peeled off the input, so that we can PCA the input. So let's training PCA. Let's take our training input and let's just dump it right into principal components analysis. No problem at all, and we can go plot that. PCA transformed data are in the X slot, and it's helpful to as tibble this guy. And the reason for doing that is that way we can drop now in the true data. Put it back in. We removed the type. Well, we're putting it back. The training $type. All right, so that's put back in, and now we can go plot it. And let's color by type. The whole point of that is now you'll have spam and non-spam marked. And there you go. You can see that non-spam is the orangish color, and it's sort of confined to this flat-ish region. And the spam is all these other outliers. It sort of matches your intuition that the spam is kind of all over the map, and most of the time when you get a spam email message, you're like, what? Well, that's why. This is consistent. Okay, well, you could go ahead and play around with this and say, all right, how do I classify this? You could, for instance, suggest that maybe I could do a k-means unsupervised cluster, but the fact that these clusters are really kind of overlapping, and the fact that k-means gives you more or less round-ish clusters is going to have a problem with the fact that the non-spam are flat. Okay, so this is why principal components analysis tells you, just looking at it, that probably a support vector machine would do a better job, because the support vector machine splits the data on a surface. Indeed, a support vector machine using a linear separating hyperplane will give you a nice linear split from spam and non-spam. So that's probably the best approach. Okay, how do you make a support vector machine? Well, that E1071 library that we loaded has support vector machines right in it. And you train them with the SVM function. So if I say SVM, I can use one of two sets of syntax. One set of syntax, which is perhaps a little easier from the tidyverse standpoint, is I can take the training input, pipe it in, and give the correct answer. Training. There's the correct answer. And you say kernel. If you want a linear hyperplane, you say linear. But I spelled training wrong. There we go. You run that. It takes a few moments, and it spits out an SVM object. Okay, sounds good enough. There's another set of syntax that is supported. This other syntax is not so tidyverse-like, but certainly works. You give it the correct answer, type tilde, period, comma, and then the data that you want to use. Does it matter? No, not really. They're both will give you the same kind of output. Okay, but how do we manage this? Well, we're going to manage this because we need to actually store this somewhere. That way we can manipulate with this trained support vector machine. So this SVM linear is the whole machine. It's got some code in it as well as some data. It knows about the parameters, i.e. where the hyperplane is, and the hyperparameters, i.e. that it is a plane, and how those planes work. Okay, fine. There are actually several other possibilities that are supported. So for instance, you can use a polynomial instead. And you could also use a radial basis function. And you could also use a sigmoid. These are the 4 different types of kernels that E1071 supports out of the box. Okay, well, how do you know how well each of these guys do? Well, it's a little tricky, but it would be useful to have a look at them and make some determination based on performance results. You can certainly plot these if you like, or you can say, well, I just want to see how they look, and I'm going to plot them against the using PCA. Certainly, that's a reasonable thing that you can do as well and get a good plot of it. Okay, fine. The problem with that is now that we've got these guys trained up, they're trained up in the original variables, not the PCA variables. So let's set those 4 aside for the moment, which we'll examine in the query, and let's just put our attention on a transformed version. Okay, well, we've got the training PCA data already. Here it is. And we can go ahead and examine it. In fact, what I'm going to suggest is I'll call it training PCA 2. Let's take the training PCA $X. Let's as tibble it, and let's add to it the correct answers, because that will be useful for further analysis. Okay, if you look at that training PCA 2, you'll see what it looks like. Pretty much looks like PCA'd data, all these principal components here, every which way. But at the very end, when we get there, there's a type column that says whether it is spam or non-spam. Okay, great. So now we're going to train a support vector machine on that. So we can take that guy, and I'll use the other syntax just for fun. So that, remember, tilde, dot, comma. PCA2. And let's give it a kernel equals linear. Okay, so now this is a linear support vector machine trained on the PCA data. Now, the support vector machines actually have their own plotting function built in, so you could just plot them using base R plot, and you'll get the correct one. Supply with it the data that were used that you'd like to predict, and tell it what you want to plot. Well, we want to plot PC1 versus PC2. If we do this, it shows you the classification. The yellow is the non-spam part of the space, and the red is the spam part of the space. You can see that this is a yellow hyperplane, and indeed, the black points here, which are truly the non-spam do get caught by the non-spam. There's a few that are in the wrong place, and the spam are successfully captured. You could do this with the others as well. So we could go take a look at what happens if we did a polynomial. And that too can be plotted. There they are. And you can see the polynomial is kind of wiggly. It was trying to capture things appropriately, but notice it's made quite a few errors. A lot of this spam has gotten marked as non-spam, and these non-spam messages got marked as spam. Oops. So the linear certainly seems to do a better job. That's not so conclusive. That's why we have the query data set. Well, one thing that's going on inside the plot function is that it's predicting using the support vector machine. Let's go back to our originally trained on the original variables. We can take a support vector machine and call it with the predict function. That predict function, then we can feed it in the query input, and it will make predictions for us. So it's saying, you know, these messages are spam or not spam. Great. Well, I think I want them all in a nice table. So I'll make a table with all of these guys. Let's say that the query type I'll call as the truth. And then after that, we have to have a bunch of columns, one for each of our different support vector machines. So we've got the linear one, and I'm going to make a copy of this so I can edit it as I go. So we have our SVM polynomial. We have our radial basis functions version. And finally, we have our sigmoidal. Okay, great. Got all those. Predict everything. So now we've got everything predicted. If you look at these query results, what you'll see, well, we've got a listing of who's spam and who's not. Clearly, not everyone agrees. And so the question is, who's who? Well, this is not so useful for tabulating results in a convenient way. Really, if we pivot longer, so we have just two columns, one which is the truth, and then another which specifies what the SVM predictor is, and then add another column that says what the predictor's prediction was, then we can do things a little more nicely. That's a little tidier. All right, fine. Great, so let's do that. Let's do that by way of a pivot. Take our query results. We'll pivot longer. Which columns are we going to use? Well, everything but the query. Everyone but the truth. Truth column. Oops. Columns equals not true. There we go. Okay, if you would take a look at that, you'll see we've got truth, we've got the name, as in the name of the particular classifier, and then the value. All right, so now we just want to find all the matches between the truth column and the value column. Sounds pretty straightforward enough. I think the best way to do that is by way of adding a column called status. And that status is all those instances where the truth is equal to the value. If you take a look, you can see trues and falses. All we want to do at that point is count them up. And we want to group by name. and we want to count the status. If we do this, you can see we've kind of got duplication of information here. Let's pick all the instances where it was right. Okay, and we don't need the status column anymore. Okay, and we can finally say, well, actually, we'd like these in percentages. So that's going to be n divided by the length of the query data. Oops. Percentage is n divided by the length of the truth column. My bad. Oops, what did I do wrong? There we go. Okay, great. And you can see the linear got 92%, the radial got 93%, and so those are kind of the reigning champions. If we go back up to our plot on the training data to help us make this determination a little better, to see what's going on, you see the radial model, how does it work? Well, it puts a blob around things. And so it has perhaps a little bit better outlier performance, but maybe these kind of things don't get caught. So although the radial seems to do marginally better, I think the linear is probably the better choice. Okay, fine. At this point, though, then you could just repeat the analysis we just did with the test data and get an ultimate performance measure. In any case, the way that these support vector machines work is by carving up the space of values. How do you train them? Well, it's very easy, using the SVM function and feed them in some data with some truth values. Provided you're careful with your data, they work pretty well. If your data overlap too greatly, or they have weird class shapes, as in the blobs of spam versus non-spam, or other classes don't match up quite so nicely, or they're more intricately laid out, then you need a fancier classifier. There are lots out there, and many of them are supported in R. Hope this was helpful.